Welcome. This is Michael. I am the creator of differential geometric algebra compute using Grassmann.jl and Cartan.jl. And this is a new research paper that I've been working on. And yeah, so we're just gonna take a look at it right now on this video here, and that's the Grassmann.jl logo with the Julia language and the exterior algebra in the logo combined. And yes, so this is the abstract. Take a look at this. Initially, Grassmann.jl and Cartan.jl introduced the DirectSum formalism into computational language design for differential geometric algebra, thus enabling the construction of custom algebras through metaprogramming. Grassmann.jl pioneered a novel type system design along with its syntax and semantics, which has undergone significant refinement through many years of development and continuous improvement. Cartan.jl represents a groundbreaking extension of capabilities offered by Grassmann.jl, marking a pioneering, fully realized implementation of numerical differential geometric algebra based on TensorField representations over a FrameBundle and the immersed topology of the FiberBundle. Grassmann.jl and Cartan.jl build on Julia multiple dispatch and metaprogramming capabilities, presenting a new computational language design approach to interfacing with differential geometric algebra based on a new sector integral theorem. This pioneering design not only actualizes but also elevates computational language syntax to new heights using the foundations of Grassmann.jl and Cartan.jl. The Grassmann.jl and Cartan.jl packages introduce pioneering computational language designs, having inspired imitation projects and thereby validating the project's relevance as significant advance in computational mathematics. So the packages Grassmann.jl and Cartan.jl can be used as a universal language for finite element methods based on a discrete manifold bundle. Tools built on these foundations enable computations based on multilinear algebra and spin groups using the geometric algebra known as Grassmann algebra or Clifford algebra. This foundation is built on a DirectSum parametric type system for tangent bundles and vector spaces, generating the algorithms for local tangent algebras in a global context. Geometric algebra mathematical foundations for differential geometry can be used to simplify the Maxwell equations to a single wave equation due to the geometric product. With this unifying mathematical foundation, it is possible to improve efficiency of multidisciplinary research using the geometric tensor calculus by relying on universal mathematical principles. Tools built on this differential geometric algebra provide an excellent language for the newly presented sector integral theorem, and also the Helmholtz decomposition and the Hodge and de Rham cohomology, for example. The Grassmann.jl package provides tools for computations based on multilinear algebra and spin groups using the extended geometric algebra known as the Grassmann, Clifford, and Hodge algebra. And the algebra operations include exterior, regressive, inner, and geometric, along with the Hodge star and boundary operators. Code generation enables concise usage of the algebra syntax. DirectSum.jl multivector parametric type polymorphism is based on tangent vector spaces and conformal projective geometry. Additionally, the universal interoperability between different subalgebras is enabled by AbstractTensors.jl, on which the type system is built. The design is based on Tensor Algebra V, abstract type interoperability from AbstractTensors.jl, with a K-module type parameter V from DirectSum.jl. Abstract vector space type operations happen at compile time, resulting in a differential geometric algebra of multivector forms. Building on the Grassmann.jl foundation, the Cartan.jl extension then defines TensorField as a subtype of global fiber for both a local product space and general immersed topology specifications on any FrameBundle expressed with Grassmann.jl algebra. Many of these modular methods can work on input meshes or product topologies of any dimension, although there are some methods which are specialized. Cartan provides an algebra for FiberBundle sections and any associated bundles on a manifold in terms of Grassmann elements. Calculus of variation fields can also be generated with the combined topology of a fiber product bundle. Furthermore, the fiber product enables construction of homotopy bundle types. The Cartan package standardizes composition of various methods and functors applied to specialized categories transformed in terms of a unified representation over a product topology, especially having fibers of the Grassmann algebra and using Cartan methods over a FrameBundle. So let's review the DirectSum parametric type polymorphism one more time. Definition. Vector space is a field's K-module. So let V be a K-module, abelian group with a plus operation, with an element 1 in K such that 1 times V equals V by scalar multiplication. So that means that there's a scalar operation built in, like this, over the field K, satisfying these distributive law and over the vector addition and the field addition, and then the associative compatibility. In the software package Grassmann, a generating vector space K module is specified as a value as some kind of a subtype of TensorBundle, which is then repackaged as a submanifold and then put as a parametric, as a parameter in the tensor algebra type system. The abstract tensors package is intended for universal interoperation of the abstract tensor algebra type system. All tensor algebra V subtypes have type parameter V, used to store a submanifold M value, which is parameterized by M, the TensorBundle choice. This means that different tensor types can have a commonly shared underlying K-module parametric type expressed by defining V submanifold M. Each tensor algebra subtype must be accompanied by a corresponding TensorBundle parameter, which is a fully static at compile time. Due to the parametric type system for the K-module types, the compiler can fully pre-allocate and often cache. Additionally, a universal unit volume element can be specified in terms of linear algebra.uniform scaling, which is independent of V and has its interpretation only instantiated by context of the tensor algebra V elements being operated on. Interoperability of linear algebra.uniform scaling as a pseudoscalar element, which takes the TensorBundle form of any other tensor algebra element, is handled globally. This enables the usage of I from linear algebra as a universal pseudoscalar element defined at every point x of a manifold, which is mathematically denoted by I or I of x and specified by the g of x bilinear tensor field of the tangent bundle on M. utility methods such as scalar. So there's various utility methods defined. Now let's focus on the next definition of linear dependence. Let V be a vector field over a field K. Then the set Vi of I is linearly dependent if and only if the sum from I equals 1 to n of Ki Vi equals 0 for some non-zero K values, for some non-zero vector K basically, or element K basically. And if that's the case, then they're linearly dependent if it's equal to 0. That's just a definition of linear dependence that it's very standard. And if we have linearly dependent set like this, then the exterior product of those is also 0. So this is now where we change to a different perspective. First, we had linear dependence in terms of this definition as this sum. Now we have linear dependence in terms of this exterior product being equal to 0. Initially, it is sufficient to understand that basically this is an operation which is equal to 0 for linearly dependent arguments. So when it's linearly dependent, then it's equal to 0. That's a very important piece of information to start out with. However, then it becomes important to understand that this is an idea that comes from extending the Grassmann's product Vi wedge Vj equals negative Vj wedge Vi. And that actually implies that Vi wedge Vi equals 0, because it also equals negative Vi wedge Vi. And for those to be equal, has to equal 0, of course. And this is how we get linear dependence by extending the Grassmann product, this wedge product here. All right. So that's the annihilation of exterior algebra and the linear dependence. So we can talk about the dimension n submanifold. So in the nth exterior algebra space of V. All right. So note that writing the exterior product V1, V2, Vn not equal to 0 implies that this is a linearly independent set. And that means that this is isomorphic to a n submanifold. Furthermore, this n submanifold forms a one-dimensional basis subspace that is induced by this n submanifold. All right. So a scalar is just a 0 submanifold. This is just kind of, the 0 exterior algebra space, the scalars, is a vector space, or, the exterior algebra space of just a one-dimensional vector space K itself. And then the nth exterior algebra space is a vector space. And we have this property that the first exterior algebra space of the nth exterior algebra space is the nth exterior algebra space. and also the 0th exterior algebra space of the nth, is the 0th of the V. So anyway, it's like these little properties you can explore. Then we talk about a way to define what the direct sum is. And here we can consider a set of linearly independent spaces. And then we have a bunch of projections with these subspaces Vi. And if we can construct this as a non-zero exterior product, then that's a direct sum. So that's one way to think about defining direct sums, but it's not so important for the computer implementation. It's just to introduce direct sums in the discussion. So now we have the grade M projection. So this is a way to talk about the exterior algebra space as its direct sum decomposition. So this is why we need to talk about introduce direct sums in the first place. So we have that the entire exterior algebra space is a direct sum of these grade projections from m equals 0 to n. And so it's the 0 exterior algebra space, the 1, and so on up to the nth. So it's the sum of all, the direct sum of all of those is the entire thing, basically. That's the point. And that's called a multi-vector space, basically. And we know what the dimension is, of course. It's based on the binomial expansion. And so the dimension of the whole thing is 2 to the n, of course. So we can look at the combinatorics of the power set. It's just something to illustrate an example, just to show we have this basis and we can have a power set of them, so we can have, different subsets of these, of the whole set of them, And so if we now apply the exterior product between these, because they're linearly independent, we can form this basis space so that they you can now apply the grade projection direct sum principle to these sub direct sums. So now this grade 2 space is a direct sum of these submanifolds, these products, and then it's part of the whole sum of the entire thing. And this is like a direct sum. So now let's talk about the M. So this is just kind of some notational stuff. So how do we define what the K module that we're working on of rank n? And we can have this kind of tuple of information that I've implemented, n, p, g, nu, and mu. And this is just to specify the presence of this conformal geometric algebra basis, which is a special case. So it's just kind of has its own special encoding that you can introduce if you want, and so this just signifies the ability to introduce this special encoding. And then we have G, which is the bilinear form, which is a metric tensor specification. And then the type of the tensor bundle NPG new mu encodes this information as byte encoded data available at pre-compilation. And mu is an integer specifying the order of the tangent bundle, which is the multiplicity limit of the Leibniz-Taylor monomials. And nu is the number of tangent variables. And n is, the dimension of the thing. So, and then this is what tells us how to generate, how many, basis vectors there are and things like that. And whether they have the conformal geometric algebra basis in them or not, and what the dimension of the space is, and so on. There's also optionally, vectors and covectors and differential operators and scalar functions that can be encoded into this tensor bundle, but it's mainly the vector space basis is what's of interest for most of what we're talking about. So the rest of the functionality is just kind of interesting extra features that you can build in, but it's not that important. And the purpose of the tensor bundle type is to specify the k-module basis at compile time. When assigned in the workspace, V equals submanifold of a tensor bundle is typically used. So the metric signature of the submanifold elements of a vector space can be specified with this V command by using plus or minus to specify whether the submanifold of the corresponding index squares to +1 or -1. For example, S+++ constructs a positive definite three-dimensional tensor bundle. So constructors such as S and D are convenient. It is possible to change the diagonal scaling with D. So S is for signature basically, and D is for diagonal. So 1, 1, 1, 0 makes a diagonal metric with a 0 in it. Although the signature format has a more compact representation if limited to plus and -1. It is also possible to change the diagonal scaling 0.3, 2.4, 1. Fully general metric tensor is a type with non-diagonal components requires a matrix. For example, metric tensor of this matrix 1, 2, 3, 4, that's an example. Declaring an additional point at infinity is done by specifying it in the string constructor with the infinity symbol at the first index. For example, the Riemann sphere has this S+++, but with an infinity prefix. The hyperbolic geometry can be declared with this empty set symbol. So, for example, S empty set +++. And then the null basis from the conformal geometric algebra uses both of them combined, infinity and empty set. And these two declared basis elements are interpreted in the type system. Then there's a tangent map which can be used to specify mu and nu, but that's not necessary to know about for this rest of the paper. To assign V equals submanifold of a tensor bundle along with associated basis elements of the DirectSum basis to the local Julia session workspace it is typical to use submanifold elements created by the @basis macro. So using Grassmann @basis s minus plus plus, or you could use the basis minus plus plus, like that notation. You know, there's different notations for it. So that invokes the Grassmann package, and it invokes this particular basis with this metric signature. The macro @basis v declares a local basis in Julia. As a result of this macro, all submanifold VG elements generated with M TensorBundle become available in the local workspace with the specified naming arguments. The first argument provides signature specification. The second argument is the variable name for V, the K module. And the third and fourth arguments are the prefixes of the submanifold vector names and covector names. Default is V assigned submanifold M, and V is prefix for the submanifold of V. It is entirely possible to assign multiple different bases having different signatures without any problems. The @basis macro arguments are used to assign the vector space name to V and the basis element to Vi, but other assigned names can be chosen so that their local names don't interfere. If it is undesirable to assign these variables to a local workspace, the versatile constructs of DirectSum.basis of V can be used to contain or access them, which is exported to the user as the method DirectSum.basis of V. Here's an example of DirectSum.basis of V, and that returns a DirectSum.basis object of V, basically. So V, when you call V with integer arguments, that provides a convenient way to define a submanifold by using integer indices to reference specific direct sums within the ambient space of V. So at this point, let me get into an example in the session here. Oops. So let's do using Grassmann. And now let's do what was the example? S minus plus plus. All right, so we've got a basis here, or we can just make a three-dimensional basis like this, just any regular one. And then we have V as a submanifold object here. And now when you call it with indices, for example 1, 3, this produces a new submanifold of that. And you could now create a new geometric algebra that's two-dimensional, which just has index 1 and 3 in it. Like this is now a two-dimensional geometric algebra, but it understands that it's a sub-algebra of the original three-dimensional algebra. Like you see, this is V13. That's the that's a multi-vector, that's an element in the multi-vector space where we omitted one of the indices, basically. So this is kind of like it's kind of a cool hidden feature that a lot of people may not know about, that Grassmann.jl has provided since the very beginning, pretty much. It has the ability to have these different subalgebras recognized, and one of the ways of dealing with it is using these indices. So this is these are the different subalgebras that you can make. And that's the that's the space, that's the parameter space, that's the parametric, that's the type that we put in, that's the object we put in the type parameter to parameterize the geometric algebra algorithms, which get automatically generated as you use geometric algebra using this programming language. So that's a little bit about generating basis elements. So the Grassmann's exterior product is an anti-symmetric tensor product. So let's try it out. So let's go back to basis 3. All right, so V1. So I made a video previously about getting started with Grassmann.jl, where I explained, that in the Julia REPL, the way you get, for example, the wedge symbol is you type \wedge, and then when you press the tab key, it produces that symbol. So, you could make a vector like this, V1 plus V2, and then you can take the wedge product, and the result will be 0, because that's a linearly dependent result, basically. So that's the calculation. And now if we make it different, now we get a different kind of result. So that's the Grassmann exterior product. So let's swap the order of that. Let's put V3 on this side. And now we'll see that this is the negative of the other one. And that's just what we're saying when we say that when you take these two vectors of one and take the exterior product and you swap the order of the product, then it equals the negative of that. And if you have the same linearly dependent vector, then it equals 0. And so this generalizes to the multilinearly determinant transposition property. That's when you have like more, it's not just basis vectors like Vi and Vj, but you have more of them. And that's -1 to the m times n. And we can rewrite this if we scrunch, the term on this side into, omega and eta, then we compact the notation. Like we say, omega is an element in the M exterior algebra space, and eta is an element in the nth exterior algebra space. So that makes for a smaller formula, basically, than this big, long formula, right? Observe that the anti-symmetry property implies that the tensor product equals 0, while the symmetric property neither implies nor denies such a property. That's just a little remark for people who want to exercise their brain a little bit. Case of third order tangent bundle operators composition. So this is just another example that the composition of these partial differential operators forms another, direct sum space like this. And because, these are symmetric differential operators, you can just think of this as being it's linearly dependent with the swapped index, right? So in order to shorten the notation, the operation symbol is left out. So what we often do is we just put v sub 1 and then v sub 2 and then v sub 3 and then v sub 1 2 or 1 3 or 2 3 or 1 2 3. That's to shorten the notation, because we don't want to write out all these things every single time necessarily. So sometimes you just put it like that. All right. So the canonical choice of orientation is with the indices in sorted order, so that, for example, the antisymmetry is applied to rewrite v sub 2 1 into negative v sub 1 2. Or the property, well, for differential operators is that they stay the same, because that's the rule. In general, permutations of the indices get rendered as orientations of -1 to the k of a basis k module. So, it's just saying that, like, if you write, for example, 2 1, it'll reorient it like that, right? So, like, if 2 3 1 or 2 2 1 3, it'll just reorient it into the sorted order. It's just to keep a canonical choice of orientation. We don't want to make things too complicated for ourselves. So, so what are some of the permutations that we can deal with? So we have this definition, which you don't necessarily need to really memorize. This is just to demonstrate that it comes from somewhere. And basically, we have this reverse and grade involution operation and the composition of the two. And we basically say that these operations form a group. So sigma 1, sigma 2, sigma 1, 2, and then the identity operation. It's a set of automorphisms, which is a grade involution and the reverse operation. And the reverse is an anti-automorphism. And what does this mean? Well, it has this property, sigma 2 of vi wedge vj equals sigma 2 of vj wedge sigma 2 of vi. So these are the operations we have. So it's a little bit abstract, but if you know about geometric algebra, you'll already be familiar with what these operations are supposed to be. So these are the reverse operation is like what would happen if you were to reverse the indices. Like when what we did here is when we did 2, 1, it would be negative. And what if we take, you know, we asked what would the reverse of 1, 2 be? Well, that would be negative v1, 2. So it just does that. So it just gives us that as an operation, as like a function that we can plug something into it, you know what I mean? And there's the other one's called involute for grade involution. And then we have the Clifford. That's the composition of the two, basically, you know. So we have these different operations that you can apply. People who know about geometric algebra will be familiar with the importance of these, and they'll be showing up later on. So we'll just keep it going. Now there's the real and the imaginary components of the exterior algebra space. And we can think of that as the sum or the averaging of basically an omega with its reverse, or omega minus its reverse, and then dividing it by 2 basically. And that gives us the real and the imaginary component. And if we do the same thing with a grade involution operation, that gives us the even and the odd components. And so this gives us this Z2 grading way to split it up into these 2 components, you know, the exterior algebra space. And in general, this can be extended to any Z2 grading projections. Grassmann.jl is a foundation which has been built up from a minimal K-module algebra kernel, on which an entirely custom algebra specification is designed and built from scratch on the base Julia language. Tensor algebra VK, where V submanifold M for a generating K-module specified by M TensorBundle choice. So in this definition, we're going to get into what is the type system in Grassmann.jl, and what are the different types and what are the subtypes, and like what is the big picture here, basically. It's the big picture of the types that are implemented in Grassmann.jl. So TensorBundle specifies generators of the DirectSum.basis algebra, and all these are TensorBundle subtypes except for int. So int is just a base type in Julia, which in many cases can be substituted in place of a TensorBundle when you just want to induce a Euclidean metric of counted dimension. So it's an integer, right? So if the integer is 3, it could induce a Euclidean metric of, 3 dimensions being counted, right? That's what an integer could do, like that. So that's why we list integer here. But we more generally want something like a signature, right? So what if we have this plus and minus to specify the metric signature? An integer is not sufficient, so we have a signature TensorBundle type. Furthermore, we have a diagonal form TensorBundle type for defining any diagonal metric. And then we have the metric TensorBundle type, which can accept a non-diagonal metric tensor array. So that covers us basically for the fully general case of geometric algebra, that if we want to induce a Euclidean metric or a metric signature or diagonal metric or a non-diagonal metric. The versatility of the Grassmann.jl TensorBundle type system is that it allows, has the expressibility for all those things. And then we have tensor graded VGK, which is a grade G element of the G exterior algebra space of V. So what does this include? Well, this could include the chain VGK. So this is like an abstract type. So this includes other subtypes. So the chain VGK is basically what many other people call like a K vector or like a grade G vector or whatever, but it just means in homology and cohomology theory, we have these things called chain complexes, and so it's appropriate to use chain here because these elements are technically also chain complex types. And so chain is a nice short word that can be typed quickly in the programming language. And technically in pure mathematics, these are part of the chain complex. So, but these are G vectors, basically. These are from the grade G. So it has the complete basis for the grade G space with the K module. Then simplex is an alias for the column module of a chain. So basically think of having like a chain which has, more chains as its K module algebra type, so that it's basically columns of a matrix, basically, and that forms the simplex. Then we have tensor term VGK, which is a subtype of tensor graded VGK, but it's just a single coefficient. So while these form a complete basis, the chain, this is just kind of a single coefficient thing. So we call them tensor term because it's kind of like it stops there in terms of tensor algebra. Like it doesn't factorize into like more basis coefficients. So it's just a single basis coefficient, right? So tensor term, because it terminates, it's terminal in terms of like the abstract syntax tree of coefficients. And so 0 is a zero value which preserves V in its algebra type. So we have 0 of V with, it's a parametric type which parameterizes V while it simultaneously expresses that the value of the tensor is 0 while preserving the parameterization of the underlying TensorBundle choice. So the submanifold VGB is basically if Vi through Vij G are the basically the basis vectors, and we have G of them. That's a G submanifold with sorted indices B. So like we said before, they have sorted indices, but if it's like 5v12, then it becomes a single. So a submanifold is just v12. This is a submanifold, right? While 1v12 is a single. So there's a difference between just v12 and 1v12, because this is just a submanifold, which is kind of like an abstract thing and single actually has a coefficient value associated to it. So like you know, like this int. So submanifold doesn't have an int associated to it. So that's what a single is. Single has a submanifold paired to like a coefficient, basically. So then we have abstract spinner. So these are subtypes of special subalgebras of the exterior algebra space. So then one of the first ones is the couple. This is a new thing, new concept I introduced into geometric algebra, like computer algebra implementations, which I came up with in Grassmann.jl. And this is what I call a couple. And a couple is basically the sum of a scalar and any other single. So which means that it basically combines a submanifold and a scalar value, and that's what I call a couple. And it kind of generalizes just like what a complex number would be, but it could be a hyperbolic number or a complex number or whatever, you know. So it's a more general kind of thing than, you know, like in Julia we have this 1 plus im. It's a complex number type, right? Oops, I have an extra parentheses there. All right, so 1 plus v1 2 in Grassmann.jl is a couple. Now it says Gaussian integer right there, but Gaussian integer is just, you know, another way of saying couple. But it's with integers basically, so Gaussian integer. So if you know what a Gaussian integer is, then you'll know what that is, but it's just another alias. But like if we do 0.1 plus v1 2 and we dump that, then we can see that it's just a couple, right? Couple has two values. Then we have something called a pseudo couple, and that is the complement of a couple. So if you have couples like 0.1, you have singles and you have couples, right? And then you take the sum of two singles and get a couple. Now what if we want to take the complement of that? That's a pseudo couple. So a pseudo couple is when you have a pseudo scalar plus a single, and that's a pseudo couple. So with the introduction of the couples, I had to introduce the pseudo couples as well. And so but pseudo couples are not the same as couples. They don't have all the same kind of properties as couples. They don't behave the same way at all. Pseudo couples are quite different in a lot of ways, but they're complementary to couples. So you can't just have, you know, couple and then somehow have it pseudo couples be the same thing. No, pseudo couples are something fundamentally different from couples, but in a lot of ways they're similar in that they're both, you know, complementary to each other. But these are couple and pseudo couple, so these are important abstract spinner subtypes that exist in Grassmann.jl, and they're built into so many different functions and stuff. They automatically output. They Grassmann.jl can be optimized, you know, when it detects that there's a couple or a pseudo couple, and it's a very nice inclusion in the type system, and it can optimize a lot of algorithms to have the expressibility of it. And this is something new that was invented basically in Grassmann.jl, including this entire type system is basically something new, but this specifically is entirely new. Like I'm not aware of any other geometric algebra implementations which would have had something like a couple and a complementary pseudo couple implementation. And then we have spinner and co-spinner, like in its fully general sense is what I'm talking about here. Like complex numbers exist, in the base Julia language, so that's nothing special. But I'm talking about the fully general approach, that how this all fits together. So spinner and co-spinner. So that's the even and the odd graded terms. That just completes the whole thing. So basically, for a lot of operations, it's convenient to be able to just specifically talk about the even and the odd graded spaces. And so that's why we have spinner and co-spinner as a specific subtype of abstract spinner. And then we have the fully general multi-vector space, which is just the complete, basis for the exterior algebra with the K module. So if we proceed further, what do we have here? We have tensor nested subtypes are linear transformations. Tensor operator VWT, linear map VW with T data type. So what this basically means is we have tensor nested, and then there are subtypes of that, which are linear transformations typically. Not necessarily, but typically it's just for the sake of most situations, that's why it's written like that. But and then a specific one is a tensor operator, and that's a linear map from basically V to W using some kind of data type T. And that's a tensor operator. So it's a very versatile type, because it can have different data types and different vector spaces V and W. So it's a versatile way of expressing linear maps. And then endomorphism is when it's V on V. It's a tensor operator, which is also an automorphism. And then we have diagonal operator. That's a diagonal map. So we have diagonal morphism and diagonal outer morphism, and these are just aliases of diagonal operators. So we only need one type, which is diagonal operator, and then we can just add more aliases of it to increase the expressibility of our type system. And then for outer morphism, that extends a endomorphism to its full exterior algebra space. So basically, if you have like this endomorphism F, and you apply F to V1, and then take the exterior product with F applied to Vn, that should equal F applied to the exterior product of V1 through Vn. And that's called the outer morphism property. And the way, if F is, this can be represented using a tensor operator, or a tensor representation of that. And so the outer morphism basically is a way of giving a representation to that more explicitly, basically. So then we have the projector type, and that's a linear map where f of f equals f is defined. And the way it works is basically the dyadic tensor product of x divided by the absolute value of x with itself. And the dyadic outer product of the matrix algebra, and that forms a projector element of a linear map. And that's like a specific type. And then another more general type is a dyadic tensor type, and that's a linear map from V with types x and y. And basically that forms a outer product like this, but it's not, it's just x and y. It's like not restricted to being like a projector linear map, but it's just the fully general, basically dyadic tensor map. All right, so this is what gives us a lot of versatility in terms of having the geometric algebra, tensor algebra basis, like the graded algebra elements, the single coefficients, the coupled coefficients, the spinners and co-spinners and abstract spinners and the multivectors. And then we have basically the linear maps, mostly like the tensor operators and the endomorphisms and diagonal operators and outer morphisms, projectors and dyadic tensor products. So the Grassmann.jl was the first to define the comprehensive tensor algebra of V type system from scratch around the idea of the V submanifold value to express algebra subtypes for a specified K-module structure. So basically this is a new comprehensive type system that was built from scratch around these different concepts, and it shows what's available here. So let's just keep it moving. Accessing a metric tensor V produces a linear map G, which can be extended to an outer morphism. So let's just take a look at that as an example. Like, let's just do the metric tensor, right? And now let's do outer morphism of that. Now this is just an identity, right? Because it was Euclidean metric. But we can see some of the things that we were just discussing in action. So this is an endomorphism with a simplex data type. And then we have a outer morphism which contains the same simplex and then extends it with the additional terms for the exterior algebra space, the full one. All right, so that's an outer morphism. And the way, so metric tensor gives you that. Metric X tensor gives you the outer morphism. So many cases it's useful to reference the full outer morphism instead of just the metric tensor as like, you know, this 3x3 matrix. Sometimes you want the full outer morphism, right? So that's why the syntax, the API gives you the option between these two, and the difference is like this one's called metric tensor and this one's called metric X tensor. And that's just what this is saying here, that accessing the metric tensor produces the linear map, which can be extended to the outer morphism given by the metric X tensor. And then to apply the metric X tensor to any Grassmann element of lambda V, the function metric can be used on the element. So for example, we have V1, 2, right? And we can apply the metric to it. So metric of that just means that it applies the metric tensor. Like if you take the metric X tensor and then apply V1, 2 to it, apply it to V1, 2, I mean. Another notation for that is metric of V1, 2. And you'll notice that the advantage is, you know, like if we do this, because this outer morphism, the way it's represented, the result of this operation ends up producing a chain instead of a single. Whereas if we use this operation metric of V1, 2, it preserves the type of it. You know, like this was a single on its input, but on the output it was a chain. But here, when you plug V1, 2 into metric, it applies the metric extensor, but it preserves that it's a the type that it was a single, basically, right? So like these values are 0, right? And that those could be discarded But when you express the operation in this way, like by applying the metric tensor as an outer morphism to v12, this is too cumbersome of an operation, right? So that's not the most efficient way to do that operation, right? You can if you want, you can do it like this. You can ask for the metric extensor, and then plug and then apply it to v12, right? But that's not the most efficient operation. The most efficient operation is this metric of v12, and it preserves that it's a single, right? Or if you have 1 plus v12, it preserves that it's a couple, right? But that was just for co-metric. Anyway, so Grassmann.jl and the Hodge complement. John Brown has discussed the Grassmann duality principle, stating that every theorem involving either of the exterior and regressive products can be translated into its dual theorem by replacing the exterior and the regressive product operations and applying the Grassmann complements. So the Grassmann complement, expressed as unary operator, which is sometimes called the right-hand rule in physics, is derived from John Brown's common factor theorem. Given a pseudoscalar v1 through n in the nth exterior algebra space, the linear map for the mth exterior algebra space element to the n minus mth exterior algebra element is the following. So this is just a way to express it. So minus 1 to the m times m plus 1 over 2 plus the sum from j equals 1 to m of I sub j. And then the exterior product where k is not equal to ij of v sub k. And then it's the grade n minus m projection of that, basically. So that's denoted the complement right operation because it's the right-hand rule. While the linear inverse, so in Julia we use the exclamation mark operator. While the linear inverse of exclamation mark is a similar map complement left expressible by reorientation. So if we're given a similar input, then minus 1 time to the m times n minus 1 times the complement right of the input element is then the grade m of the grade m projection input element, then produces the complement left output. Together these form an orthocomplementary propositional lattice, which can be, expressed using something like De Morgan's laws, where the regressive product satisfies the Grassmann laws with the, the Grassmann complement and the exterior product. So what you can do is we have our three-dimensional basis. So the complement of V1 So we have complement left and complement right. We have these different operations, and they just basically reorient the result and change us to an n minus m space. Then we have the Hodge complement, which is expressed as unary operator star, and we define it as a composition of complement right and the metric as a linear operator. So star equals the complement right composed with the metric. as an outer morphism. This linear operator is also called complement right Hodge, or only Hodge. So now we have Hodge, or complement right Hodge. Complement right Hodge, or star. So here Hodge for Euclidean metric, it's not going to make much difference from using the exclamation mark, because it's the metric was the identity metric. The original Grassmann complement is equivalent to the Hodge complement with the Euclidean metric tensor, making metric an identity. So like I just said, when the metric is an identity, then the difference between this Hodge complement and the right-hand rule, there's no difference between them. The interior contraction is the regressive product of eta and star omega. Is defined in terms of the regressive product and the Hodge complement. By default, the right contraction is used, which I denote here with the greater than symbol. But there's also a left contraction with the swapped arguments. And then in some other literature, there's different kinds of contraction conventions. And that convention is accessible here as well, and with a double symbol instead of using a single symbol. If you do a double symbol, then that's the alternative convention where the reverse is applied on the input, and by applying that, it results in their convention. And then so that's the interior product. So an example is, the inner product of something like this, or like the inner product of two vectors. Right, so that's a vector, and then take the inner product of those, right? Another way to get that result is like this, right? So that's the definition, right? The regressive product with the complement. So, and because it's a Euclidean metric, we don't need to use the Hodge complement. So you could take an inner product like this if you want, but there's an actual inner product operation built in. Using coupled subspaces in the block matrix structure of metric tensors, a basis element can be factorized in a corresponding way. In particular, for the diagonal metric, this is simply the basis factorization. However, a non-diagonal metric induces a more complex block factorization. So this leads us to the definition of the Clifford geometric product. So if AI is an indecomposable basis element with regards to the block matrix structure of the metric tensor, and B is a grade K exterior algebra element space, graded element, then define the operation O minus as either AI O minus B equals AI wedge B plus AI contract reverse B, or B O minus AI equals B wedge AI plus reverse of B contract AI. Now we're gonna stick with this case, so there's like these two cases, right? And for the rest of the definition, we're just going to stick to the first case. If A is like A1 wedge, up to AM, our basis factorization, then the geometric product of A1 to AM is equal to the exterior product A1 to AM, because we're able to, form a basis factorization of those. Furthermore, if A1, if the geometric product of all these can be, the geometric product of capital A times B can be expanded. So we're going to take this exterior product, this geometric product, A times B, and it can be expanded in such a way that we first do A sub M times B, right? And then we can apply this rule. And then we can take the result of that and use A sub I and apply it again, right? So it's like a recursion rule, right? So we can recursively apply it. And it can be expanded to distribute the operation of A times B. So that's for the fully general way with respect to the block matrix structure for the factorization of the basis elements. All right? And by applying this principle with the distributive law over the entire exterior algebra basis, the Clifford product is defined. And in Julia, the multiplication symbols, like the regular star symbol, can be used for geometric products, right? So V12 times V1, right? So like 1 plus V12 times, 1, 2 plus, 3 V12. That is like complex multiplication, like complex number multiplication, right? Because the result is still a couple. Let's make it like so like you see it still is a couple, but if we change the indices, now it's a spinner. Or a quaternion, right? So now it's a quaternion. Quaternion is actually... Oh, I forgot to... did I mention it in the paper? I don't know. But quaternion is like another alias for spinner, right? So... yeah, so quaternion is this... That's with the geometric product. Oh, here we go. So like if you do the multiplication like this, then it remains a couple. But if you do the multiplication like this, these two couples multiplied become a quaternion, right? So the Grassmann.jl package is so expressible. Like I believe I've seen other implementations that have it like in its fully general sense like this, like for any generated algebra that you want to generate right at your fingertips. You can have this feature where like you can have these two different complex number subspaces, and then they can be like separately treated as complex numbers. But then once you suddenly make them interact with each other, they become quaternions, right? So you could be doing something like complex number stuff in this two-dimensional subspace, complex number stuff in another two-dimensional subspace. And then at some point you like combine them and multiply them or something, and then they become quaternions. And if you were using Grassmann.jl while doing that, it would just automatically upgrade you suddenly from these two-dimensional numbers that were treated separately to now these quaternions, which are unifies those, right? So this is a very powerful like way of doing it. That's with a geometric product an example. So yeah. So for example, for any vi in the grade 1 space, we define vi squared equals vi times vi, which equals gii. So that's from the metric tensor, right? So typically the diagonal metric G of the algebra is often defined by relations like this. So you could define a geometric algebra using the diagonal metric relations, for example. Then there's a null basis of the projective split. And that's basically when you have this V sub infinity and V sub empty set, and that one is like, we define like this plus or minus metric, and then we take the sum or the difference of those, and then we scale them appropriately, and then that produces a Lobachevsky plane, but with a transformed basis representation. And then the geometric product, then the metric tensor is transformed from a diagonal metric to a non-diagonal metric. And this non-diagonal metric transformation of the Lobachevsky plane produces this new geometric algebra. The geometric product behaves a little bit less intuitively. It's still the same rule, the definition that I give up here, but it behaves less intuitively than what most people understand typically in this particular case with the transformed null basis. And then we have the geometric product can be applied in two averaging operations, which are symmetrization and anti-symmetrization operations. And this is been discussed previously in some of my other, videos and papers and stuff. And we'll just keep it moving because there's a lot to discuss. So the reversed product. So consider the reversed product. So the reverse of an element times itself. So typically we think of the absolute value squared as that. And so the absolute value is the square root of this thing. And there's like a Euclidean norm of it as well. Like sometimes you want to emphasize that you want to restrict to the Euclidean case, so then you can put like a double bar if you want. But in general, the square root is like computed with this logarithm for any invertible omega, but this is the square root of like this geometric product, right? And then this is just like get you started. A simple way to calculate the algebraic inverse is the reverse of an element divided by basically this absolute value squared. And that's one way to do it. So the sandwich product is basically this operation right here, eta O/omega. So this is just my notation of it, in which case you take the involute and then the inverse and then sandwich it with eta in the middle and then omega again. But there's the alternative notation, which is the reverse definition, which is eta omega times the involute of eta inverse. And that's with these triple arrows. And this is what some other what the Clifford Python package uses. So a lot of people who use the Clifford Python package might be familiar with that convention. But I don't believe this is like a appropriate default convention. I'm not opposed to it existing, so you can keep using this symbol if you want. But I think there's room to define the correct convention, which is the O/ symbol, which is the opposite convention. There's basically two ways to do it. You can order the orientation. You can orient it one way or orient it the other way. And one is basically clockwise and the other is counterclockwise. And I'll get into it a little bit later again. And so now these are just some nice extra there's just some like fun little exercise regarding formulas regarding the absolute value of the real part squared and the absolute value of the imaginary part squared, and how you can think about those. And then, yeah, this is about the square root of -1. This is, some people like to, you know, wonder about the mystery of the square root of -1 and so on. And so I've just included some fun little formulas involving the square root of -1. And then I have this fun little formula right here, which is if you take the reverse of omega times omega, which is the absolute value squared, and you split omega into its real and imaginary parts, then it splits like this. It's the real part squared plus the imaginary part squared plus 2 times the real of the real times the imaginary. And this a new formula. I don't believe I've seen this as a formula somewhere else before, so this is like a cool new formula, I believe, that I came up with. So yeah. So now let's just wrap this up in a moment here and take a look at these formulas here. So we'll just take a real quick drink some water. All right, so let omega be a grade M element, then the regressive product of I with omega is omega itself. And here's a little proof of that. I've discussed this before in the past, so if you're interested in that, you can take a look at it in the paper. I'll just keep it moving. Now, if we observe that star omega equals the reverse of omega times I equals the inner product of I and omega. Since the inner product of I and omega equals I times the regressive product of star omega, and we just proved that the regressive product of I and omega equals omega, so that equals star omega. So it's just a cool little thing that I found, like, it helps me think about it. Like, I don't know, I haven't seen other people think about it like that, but this is like how I think about it. So yeah. And then we have the theorem, let omega be a grade M element, and the complement of a complement equals -1 to the m times n minus m of omega times the absolute value of I squared. Now this is called the complement of a complement theorem, and I've discussed this previously in another video on YouTube and in my paper in the past and on different occasions. And so I have a proof of how to think about it. So I've discussed this particular proof before. I've included it here as again for reference for people to familiarize themselves with some things about it. But we'll just keep it moving for now since I've discussed this before. The Euclidean complement of a complement. So the complement of a complement -1 to the m times n minus m times omega, since the absolute value of I squared equals 1. So basically the difference is that in the Euclidean case, the absolute value of I squared equals 1. So we can basically drop it, right? So that's the difference, basically, you see. So the fully general case, there's a difference between the Euclidean and the fully general case. So let omega be the grade m element. Then the inner product of omega with itself times I equals the outer product of omega times its complement. So this is a rather interesting theorem because it relates a regressive product with a complement and the exterior product with a complement of a element. So it's an interesting, result in mathematics, I think. So I provide like this proof of how to think about it here. And I believe I've discussed this before in several other videos and other places or whatever. So, and papers and whatever. So I've included it again here as well if people want to check it out. Here's some more interesting results, like the exterior product. This is a more these get progressively more general. Like we just start out with like these simple expressions and they get progressively more general. Like this is a omega element with itself. Now we think about the more general case. What if eta and omega are not the same element? And the more progressively general it gets, the expression gets more complicated. And I have discovered what the general case is and included it here for a reference if people are interested in it. And this is another simple, corollary, but just some extra information to strengthen understanding about, like the inner product of an element times I equals the reverse of it times the exterior product with its complement. And there's like these different things that are equal to each other, right? So we'll just keep it moving. And then we have this important table, the Grassmann's graded tensor right contraction is written with this greater symbol. So that's the one I discussed before. That's the right contraction, Grassmann definition. And so that shows up right here. And in terms of geometric product, it's the reverse of eta times omega, and it's the grade r minus s component, right? And then there's the left contraction, which is the opposite. And I have this full table for people who use different conventions, like the Grassmann right convention. Like some people, you can use the geometric product to figure out what your convention is. Like if using your geometric product, this is your contraction operation, then you need to use input like the reverse of eta, and then that gives you like that, because eta would have to be reversed from this between these two formulas, right? The difference between these two formulas is eta's reversed here and it's not reversed here, right? So whether eta is reversed or not, or omega is reversed or not, that's what the difference is between these in the table, right? And so that's what the difference is between these different conventions. And so this is the important one, I think. So, and then some other people might want to use these other conventions depending on what it is they want to do, right? So the common unary operations on the tensor algebra elements. So we'll just quickly, so here's a table of running through some of the operations. Like if you ask for the manifold of an element, like let's say you have 1 plus v1 2, right? if you ask for the manifold, it gives you, the submanifold corresponding to that element. mdims is like the dimension of the submanifold. mdims, manifold dimension. gdims, dimension of the grade, if it's a graded element. Grade returns the grade of the element. Is tensor, is it a tensor algebra element? Is graded, is it a tensor graded element? Is it a tensor term element? Complement right, complement left, complement right Hodge, complement left Hodge. Metric extensor, cometric, involute, reverse, Clifford, conjugate, even and odd, real and imaginary, absolute value, norm, unit, normalization, scalar, vector, bivector, trivector, pseudoscalar, value and value type. So this is just like a nice summary of some of the operations. Now, what are the binary operations? Like the plus and minus operation, then the wedge product and the V product, which is the exterior and regressive product. Then the right contraction and the left contraction, the geometric product and division here. Then we have this O/, which is the sandwich, and then this triple arrow as the alternative operator orientation. And then related to tensor operators and roots of polynomials, we have the inverse. That's like the inverse of a matrix, basically. The determinant, the trace, the transpose, the compound matrix, the outer morphism, the operator of a representation of something. So we'll see how that works in a moment. But if we have like 1 plus v, 1, 2, we can get like the matrix operator representation of it. And the companion matrix of a monic polynomial, and then we have, the roots of a polynomial, or the real and the complex ones, the monic roots, characteristic polynomial of a determinant of the characteristic matrix, and the eigenvalues, the real and the complex, eigenvectors, and so forth. These are just utility functions. But these are all custom methods that are for the tensor operator types that are included. Some custom algorithms partially as well. So for a lot of these, well, most of, So TensorField, topology, and FiberBundles. So the commonly used fundamental building blocks are the product space, which is an abstract array of grade 1 chain elements, and that uses the Cartesian products of interval subsets to generate a lazy array of point vectors for input ranges. For example, you have this 0 to 1 using 0.1 intervals, and you take the product space of both of those, like twice, right? That creates a product space of both of those using V as the parameter. Or you can leave out V. You don't have to specify V, then it gets auto selected, right? This is just something. A global represents an array with the same value at all indices. It's just something that was kind of convenient to include. And then local fiber has a local base type and a fiber type. for the trivialization of the FiberBundle. And in particular, there's also the coordinate with the point type and the metric type. And then one of the innovations in Cartan.jl is the immersed topology, which is a type that handles the topological information for differential topology, and combined with the other differential geometry functionality, the immersed topology is a key aspect of enabling doing differential geometry in various topological spaces. And so the immersed topology, so we have the basic product topology, we have the simplex topology for continuous simplices, there's a discontinuous one which disconnects the topology, there's a Lagrange topology using the Lagrange polynomial base, and then there's the quotient topology, which defines classes of quotient identification, in particular for product topologies. And this is a more complicated type which define, so we'll get into it. All right, so generalizing upon product topology, the quotient topology defines a quotient identification across the boundary fluxes of the region, which then enables different specializations of quotient topology. So then we have basically an open topology where all boundaries don't have accumulation points, a compact topology where all points have a neighborhood topology. Then we have a cylinder topology, which is like a closed ribbon with two edge open endings. And then we have a Mobius topology, which is a twisted ribbon with only one edge open ending. And then we have a wing topology, which can be used for upper and lower surface topology of a wing. We have a mirror topology, which has a reflection boundary along a mirror basis axis. And we can have like a clamped topology where each boundary face is reflected to be a compact topology. Then we have a torus topology, which is generalized compact torus up to 5 dimensions. And then we have the hub topology, which is a compact topology of the hub fibration in 3 dimensions. And then we have a Klein topology, which is the compact topology of the Klein-Bodel domain. Then we have a polar topology, which is the polar compactification with the open edge boundary. And we have a sphere topology, which generalized mathematical sphere is compactified. All right. And then we have alternatively a geographic topology, which has its axis swapped from the sphere topology in 2 dimensions, because mathematicians prefer the sphere topology to be expressed one way, and for a geographic topologist, we might want to have it expressed in the opposite convention. And so the combination of point array and coordinates and immersed topology leads into the definition of the TensorField as a global section of a FrameBundle. So what are some of the, here's some methods associated to that. So these are methods that apply to a simplex topology except for the is open and is compact. So is open is true if the quotient topology is an open topology instance, and is compact is true if the quotient topology is a compact topology. But in general, the rest of these now all apply to simplex topology instances. And so for a simplex topology, we're just going to review what are some of the kind of utility methods associated to it. So we have like nodes, which counts the number of vertices associated to a simplex topology. And we have sdims, which counts the number of vertices n of a simplex topology locally, right? And then the sub-elements, which is the subspace element indices associated to the full topology, which is referenced below. And then there's the sub-immersion, which is modified with the vertices re-indexed based on the subspace. So there can be like a subspace topology, right? So we could have like a simplex topology and a subspace topology, right? So the sub-immersion re-indexes it according to the subspace topology instead of using the global representation. And then we have the just the topology view into the full topology based on the sub-element structure. Then we can access the total element counts of the total number of elements in the full topology. And we can count the total number of nodes, which counts the total number of nodes over all subspaces. And then we have vertices, which is a list of indices associated to the subspace immersion. And then we have the elements, which counts the number of sub-elements in the immersion. And then there's the function is full, which is true if the immersion is a full topology but not a subspace. Then we have is total, which is true if full topology is covering the total nodes completely. And then we have is cover, which is true if is full and is total is fully covering the total nodes. Then we have is discontinuous, which is true if an instance of for an instance of discontinuous topology, whereas is disconnected is true for a discontinuous topology that is fully disconnected. Then we have the continuous function, which transforms the original data from a discontinuous topology, and the discontinuous function, which allocates a derived discontinuous topology. The disconnect function allocates a disconnected variant of a discontinuous topology, and the getFacet function helps with indexing sub-elements in reference to the full immersion. The getImage indexing vertex subspace is in reference to the full immersion. Edges assembles a simplex topology 2 of all unique edge elements. And the facets assemble the simplex topology of all unique facet elements. Complement returns a simplex topology based on the sub-elements, which is complement space. And the interior returns the interior component of the simplex topology. The boundary operator returns the boundary component of the simplex topology, whereas the degrees returns the graph degree for each incidence of the vertex. The weights divides each incidence of the vertex by the graph degree, and the adjacency matrix returns a symmetric sparse matrix with ones at the vertices, and the anti-adjacency returns a sparse matrix with vertex anti-symmetry. An incidence relation is a heterogeneous relation for vertices and elements, and the Laplacian can return the graph Laplacian for adjacent vertices. The neighbors function finds neighboring elements per simplex topology facet. Now let's get into manifolds. An n-dimensional manifold M requires existence of a neighborhood U for each P in U, so that for each P there is a neighborhood U subset of M with a local chart map which is phi, and given another chart map psi, then there is the combinatorial composition where you take phi and the inverse of psi, or psi and the inverse of phi, and this combination of composition are called the transposition maps. And now, given all the charts, if all the transition maps are CR differentiable and the union of these neighborhoods forms the manifold, then the collection of charts is called an atlas of a R differentiable manifold, right? So a FiberBundle is a particular kind of manifold E with a projection pi from E onto B, which commutes with local trivializations phi paired to neighborhoods U phi of a manifold, So B is like the union of a bunch of these neighborhoods, right? And then we have these local trivializations phi, which help us map into B. And so B is the base type and F is the fiber type. And EP produces is basically when you do the pi inverse of P, which is a Cartesian product of the set of P with F, the fiber type. Okay, and so the E is the total union of all those fiber spaces. Okay, and so that's what a fiber bundle is. And when we have a fiber bundle, it's actually an abstract type, and so we have specific instances of it that are like different kinds of subtypes and stuff. And so another abstract type is called coordinates. So we can have like a coordinates, like things that are coordinates, and one of those is called a point array. And the point array has a point type and a metric type. There's also a fiber product, which introduces a fiber product structure for manifolds. But for most situations, we just deal with a point array, right? So, but there's like more you can do, like you can have fiber products and so on. Then we have the frame bundles, right? So a frame bundle has a coordinate type of C and an immersion. So it extends basically the coordinate structure using the topology, the immersed topology. So the topology of an immersion, right? And so the instances of those are, for example, like the grid bundle, which is an n grid with the coordinates and an immersion. And then we have the simplex bundle, which defines also coordinates and an immersion. But these are different kinds of things, you know, grid bundles and simplex bundles. And face bundles, which defines the element faces and the immersion. And then we have fiber product bundle, which extrudes dimensions from simplices. And homotopy bundles to encapsulate variations as frame bundles. And these help with, you know, with most frame bundle, like more could be defined in the future, you know, but basically frame bundle is like this abstract type that helps deal with that under which we can stick all these different things, right? We can put all these different ways of thinking and put them under frame bundle. Okay, so like grid bundles, simplex bundles, face bundles, fiber product bundles, homotopy bundles, these are all different ways of thinking about fiber bundles. And frame bundle is we just like all this different junk of way of doing things, we'll just all put it under frame bundle, right? Because that's what it all belongs under. But yeah, anyway, so TensorField defines fibers in a global section of a frame bundle. Okay, so when we have all this frame bundle stuff defined, then we can define a TensorField as fibers by defining the fibers in the global section. Okay, so when a TensorField has a fiber type from the exterior algebra of a tangent space, then it is the grade G differential form on the tangent bundle of V. In general, the TensorField type can deal with more abstract fiber types varieties than only those used for differential forms, so it doesn't have to be from like the tangent bundle, right? Exterior algebra on the tangent bundle, but as it unifies many different forms of tensor analysis, but it's like very general, right? But in those cases we have differential forms. By default, the induced metric is defined globally in each point array unless a particular metric tensor specification is provided. When the default induced metric is invoked, the metric tensor from the tensor algebra V type is used for the global manifold instead of the extra allocation to specify metric tensors at each point. So the frame bundle then defines local charts along with the metric tensor in a point array and pairs it with an immersed topology. then the fiber of a FrameBundle section is a fiber of a TensorField. And so the way this works is basically we take the local trivializations and bundle them into a FiberBundle, but then we pair it with the FrameBundle information. Like it's a lot of different information, and basically the induced metric is just basically uses the algebra default metric, so that's for most people what they gonna deal with. But but we'll have examples with other things, more general metrics. So what are some of the other functions? So related to frame bundles and TensorField. So like the coordinates returns the coordinate, and then the coordinate type return applies to the fiber bundle, so the local fiber, and similar for the immersion returns the ImmersedTopology data, the immersion type. And then we have base and base type, fiber and fiber type, points and points type, metric tensor and metric type, full coordinates, full immersion, full topology, full vertices, full points, full metric extensor. And so the reason why we have these like full variants of everything is because we could be dealing with like a subspace topology of a frame bundle on a frame bundle. Like we could be dealing with a frame bundle which has a subspace topology, but we want to be able to access the full thing. When we're dealing with a subspace topology, we want to be able to recover the full information, right? So that's one way of doing that. Then we have this important function, is induced is true if the metric type is an induced metric type, and then bundle returns the integer identification of the bundle cache. And then there are various methods also for interpolation that can be invoked by applying TensorField instances as function evaluations on base manifolds, or applying some form of resampling method to the manifold topology. And then we have also volumes, returns the face bundle with simplex volume at each element. Init mesh provides an API keyword for interfacing with mesh initialization. Refine mesh provides API keyword for interfacing mesh refinement. Affine hull returns localized affine simplex hull at each element. Affine frame returns a localized affine basis frame at each element. And gradient hat returns the hat gradient for the simplex bundle. So for the grid bundle initialization, it is typical to invoke a combination of product space and quotient topology, while optimal Julia packages extend simplex bundle initializations. Optional Julia packages extend simplex bundle initialization, such as meshes, geometry basics, Delaunay, QHull, mini QHull, triangulate, TetGen, MATLAB, and flow geometry. So now let's get into some of the differential geometry functionality. So let gamma be a curve, gamma of t with parameter t. We can define the integral of the interval map as a cumulative trapezoidal sum, and integrate would be like the final value of this integral on the interval end, right? So there's two functions, there's integral and integrate. So integral gives you like the functional, like the function as the result as like a function of t, right? The integral is a function of t, and this gives you the final value. Integral and integrate. I figured you could have integral as one word and integrate as another one. Like there's like two words that you could have in the programming language, right? So this is like a new idea I came up with. Like I don't think I've seen it before. I don't know if other people have done this, but I think like if you have integral and integrate, you could have two different functions. One of them gives you like the integral as like a function, and the other one gives you the integral as the final value. And then you have the arc length, and that gives you basically this curve parameter s of t, which is basically this integral of the speed of the curve, and that's called the arc length, right? So then you have the tangent, which is the tangent speed curve, which is, you know, notated like this. And then you have the unit tangent, which is the unit tangent curve, the gamma dt, you know, dt ds, unit tangent speed, right? Then you have the speed, which is the tangent speed of the curve. Which is ds dt. And then you have the normal. So if you like study the differential geometry of curves, you would be familiar, or like just some calculus or whatever, you might be familiar with these things. So like the normal of a curve and the unit normal and the curvature. So like the curvature is like kappa of t, and then you can have like this formula like that there's this unit normal, and that the normal is the product of the curvature and the unit normal. So we have, but there's like, in terms of the API, what Cartan does is it provides you all these functions so that you can get the normal of a function, or you can get the unit normal, or you can get the curvature, right? So it provides you all that. So like the radius, which is the inverse of the curvature, and then there's the evolute and the involute, which is of interest to some people studying, you know, geometry. The osculating plane, which is the linear span of the tangent of the normal, and the unit osculating plane. The binormal, which is the complement of, you know, that span, and the unit binormal, and the torsion. And then there's basically the frame. And so some of these, so these can apply to abstract curves in any number of dimensions often, like the frame. Like if you want a scaled frame or a Frenet frame, like a unit frame, this gives you a unit frame for an abstract curve in any number of dimensions. The formula here is written for 3 dimensions, but the functionality in the programming language, in the programming here, actually automatically works in any number of dimensions, okay, for abstract curves. And then it can give you the curvatures in any number of dimensions. Like it doesn't just have to be the curvature and the torsion. It could keep going in higher dimensions, okay? Then there's the bishop frame. Now this is specific to space curves in 3 dimensions. This computes the bishop style frame, okay? If you're familiar with what the bishop frame is, then you'll appreciate that this functionality exists. Okay, the bishop unit frame. Okay, these are functionality related to the bishop frame, which is specific for 3 dimensions. And then there's the plane curve function. So given the real function of which is the curvature and an angle, it produces any plane curve, okay? It's a fundamental theorem of plane curves. Then there's the link map, which we'll see in action later. And the link number, which is proportional to a sector integral of the unit link map. And we'll take a look at that later as well. All right, so now the surfaces surfaces gamma. So we have like surfaces which could be parameterized using two parameters, right? But they exist in 3 dimensions. So the graph outputs a surface from a scalar field. So suppose you're like given the scalar field and you want to make it into a surface. Graph is like the function that transforms a scalar field into an actual surface, okay? So the normal vector n of x is basically of a surface, right? So you might be familiar with a normal vector, right? So unit normal, okay? That's the normalization of that. Normal norm is the norm of the normal, okay? Jacobian is the linear span as the tensor operator of the, and then the Weingarten is another linear span, but this time of the unit normal, okay? And then we have something new. This is what I call the sector determinant. So this is basically the exterior product, okay? And that's what I like to call the sector determinant, because it's shows up in the sector integral, okay? So the sector integral is the integral of the sector determinant, okay? And so we're gonna discuss it later, okay? But this is just summing it up, okay? The sector integrate estimates the total value of sector integral. Area is a cumulative, integral for computing the hyper area of a hypersurface. And surface area estimates the total value of the surface area integral. And then surface metric gets the grid bundle with the first form as the metric tensor. And the surface metric diag gets the grid bundle with the first form diagonal metric. And the surface frame constructs an intrinsic orthonormal surface frame. And then the other frame function is a scaled Darboux style frame. Okay, and the unit frame is then this right here. That's the Darboux frame. Then the first form is the metric tensor, okay? When you have a surface gamma, okay? Second form, alright, the unit normal and the surface gamma. Third form is the composition of the first form and the unit normal. Shape is the geometry of the shape operator, which is the inverse of the first form times the second form of a surface gamma. And the principles are the principal curvatures, are the composition of the eigenvalues in the shape operator. And the principal axes of the curvatures are the composition of the eigenvectors in the shape. Or the shape and the eigenvalues, yeah. And the curvature polynomials are the composition of the shape of the eigenpolys, which was mentioned in the functionality earlier for eigenvalues. And then we have the mean curvature, which is the first curvature of the shape. And then we have the Gauss intrinsic curvature, which is the last curvature, and the Gauss extrinsic curvature, which is in the sector form. And the Gauss sign is the sign of the Gauss curvature of the shape operator. So that leads us into abstract tensors and Grassmann settled on custom trigonometric identities. So the exponential, for example, can be expressed as a series like this, and the logarithm as a kind of series like this. Now, this doesn't mean that every evaluation of the exponential or whatever like gets evaluated this way, but these are just some fundamental identities that help in the most general case, like calculate when we don't have like another way of doing it or something. So this table, these custom identities have been built into the programming languages as fallback cases. But if there are more special algorithms that are known later on, they could, replace these some of these, general rules or whatever. So let's get into interactive computational sessions. So when using Grassmann, so like we have using Grassmann here, the Cayley table can be used to recall geometric algebra information. For example, to compare the contractions or something like that. So there you go. That's like one of the Cayley tables right there. And that's when you want to compare like the two contractions, right? So you could compare it you could specify your geometric algebra and get the operation, binary operation, and then get the Cayley table as a result of that. So one of the things that is important is the linear system of equations, and I've discussed this previously in other videos and other papers and presentations and so on. So you can solve a linear system of equation explicitly using exterior algebra. This is x equals this is the result, right? So we remark that the Grassmann methods for low-dimensional linear systems are more numerically stable than the Julia-based linear algebra methods, and they're fast. So let's do this example here. 1, 2, 3, 4, backslash 5, 6. So we ask Julia, and it's gives a decent answer. It's not exact, right? But okay. Now we try the same thing using a tensor operator. Okay. So what does this mean? It means it's exact, right? We don't have these little round off errors. All right. So that means using only exterior products, there is an explicit solution to the linear system by allocating and then calculating the exterior products and then taking the permutations with P0, right? Since the exterior products are oriented, it is sufficient to check the orientation of the hyperplanes with respect to the reference point for determining whether P0 is a point contained in the simplex. Thus, it is sufficient to check the orientation of all the same exterior products as when solving the linear systems. While calculating a linear inverse of the linear system involves only a partial application of this principle and requires also allocating the transposed dyadic result. So the point is that there's this kind of overarching narrative regarding exterior algebra and how it's used to solve linear systems, and then you can use that to check information regarding the whether a point is contained in the simplex, right? And then when you want to solve the linear inverse of a system, there's a similar calculation involved in that. This what I've described in several times before characterizes this in using the Grassmann algebra formalism. Okay. Furthermore, the this operation for solving the linear system p\p0, right? It is a partial application of this with the action of an operator. So consider the operator composed with inverse, right? So let's take, for example, b equals v12 plus 2v13 minus 3v23. And if you haven't done so, we need the three-dimensional basis, right? So then when you ask for the operator of B, this matrix you get. Now, if you ask for the inverse of the operator, and then you ask for the operator of the inverse, okay? You see what's going on there? So we're solving the linear system on a representation of an operator, and we can either invert the operator before making it a matrix, or we can invert it after making the matrix representation, okay? All right, so let's get into plane curves. So let t be the parameter on the interval from 0 to 4 pi. So let's get into some examples. So for this example, we're going to need all right, so let's define t. Sorry about that. All right, so we have t, so we have a TensorField. So now we have this parameter t. Okay, let's reorient this like that. Let's put it like that, okay? So let's take a look at, see that? So we can plot different functions, right? So lines is like the Mackie function for lines, but this is like a tensor field from Cartan package, okay? These are just real functions in this case, and we're about to make plane curves. Okay, so that's our plane curve. That's the one depicted here, at least, so. And then we can add a unit frame to the graph. There you go. So this is like the two-dimensional unit frame basis, right? So yeah, arc length. This is the arc length of the curve, right? So we had this curve, and then this is the arc length. And this is the speed of the curve, okay? So it's not a constant speed curve. This speed of the curve is varying. And this is the curvature. Now here's where we can apply the fundamental theorem of plane curves. You can get a plane curve from a curvature. And if you if you add like another parameter, it rotates it. Like it adds like an initial rotation to it. Okay? But by default it's doesn't have any angle, okay? Oops. So these are some interesting plane curves that you can investigate. Alright, so now we're going to observe vector fields by integrating streamlines. Okay, so we're going to define this Lorentz thing, which gives us, which parameterizes this vector field, okay? For for this example. Then we're going to define P. And then here we specify the parameters of the Lorentz partial the Lorentz differential equation. And then we apply. So what is VF? VF is like a vector field, okay? So let's plot it. Stream plot VF, grid size 10 by 10. Oh, grid size equals, okay? So this is from the Lorentz differential equation. When you pick like certain parameters for the differential equation, then you get a vector field like this, okay? When in a certain range of, in like a when the range of values is like within this cube, okay? And in the text here, you can't really see. You can just see a two-dimensional depiction of it, but when you have the interactive session in Julia here in the computer, you can turn it around and get a view of it, you know what I mean? Using the mouse, you click around a little bit, and the keyboard controls are there as well if you want to use the keyboard to manipulate it. Well, that's just the Mackie software, you know, visualizing streamplot. Anyway, I'm getting carried away. But the point is that this is a numerical representation of a vector field, and any vector field that we numerically represent can be plotted here. And so one of the things, examples here, is the ODE solver in the Adapode package. So this is built on Cartan as well, provides both the Runge-Kutta and multi-step methods with the optional adaptive time stepping. So let's do an example of that. So we'll define the function as like this, 10.0, right? 60.0, 8/3. And then we'll define x0 then we'll define the initial condition. Okay. So this produces like an initial condition object for the differential equation solver, okay? Once you have an initial condition object, then you can, you know, solve a differential equation, right? Then we just pick a solver, multi-step integrator, fourth order, 2 to the minus 15 step limitation. All right. So that solves gives a solution. And how does this work? Well, we're just visualizing it with the Mackie software. But if you just run ODE solve by itself, this produces a Cartan TensorField, okay? So all these things are TensorFields, Cartan TensorFields, okay? And the Grassmann package is used as the foundation, like all these vectors and stuff, they're Grassmann elements, okay? They're three-dimensional vectors in Grassmann algebra, okay? And then the whole solution of the differential equation is a tensor field in the Cartan package. And the Adapode package has a differential equation solver, okay? As an example, like all right, so let's get moving. So let's recall this is just some more text information from previous things I've written before. We'll just recall that there's like the first grade sandwich product, reflection by the hyperplane. I talked about this proof. I thought this is a pretty cool proof because it uses the geometric product, and you can think of it splitting up the way you can do this calculation. So it's a really nice proof, and I've discussed it before elsewhere, so I'm not, and then we have a lot of other information to discuss today, so I'll keep it moving for now, but there's a lot of interesting things going on here. Then there's the Cartan-d'Audouin theorem. For every isometry, there is a way to express it as a composite of at most k reflections. Hence, there exist vectors nabla j such that, like this, okay. So yeah, this is a classical theorem. Just reviewing it here using this operator notation, okay. So this is stuff I've discussed before, like note that the elements of the transformation of this group preserve the inner product relations. The even grade operators make up the rotational group. Each bivector isometry is a composition of two reflections, okay. So the exponential map and the Lie group parameter special cases. This is a common special case when you consider the differential equation with its solution with the exponential map. And you have this Lie group parameter that you can think of as being 2x. Then you have this hyperbolic cosine and hyperbolic sine, or the cosine and the sine in the 1 plus theta omega. These are some of the special cases for the exponential series. And yeah, so this is just more information about the convention of the sandwich product, which I've discussed before in the previous presentation. But the sandwich product must be written with the reversion on the left side, otherwise the rotation is clockwise and opposite of the phase parameter convention of the Euler formula. For example, here's an example that you can take a look at and verify for yourself, so that it's rotating in the wrong direction, opposite of Euler. Whereas in this convention, it's in the correct Euler convention. So the sandwich, so we can take this insight and apply it to the sandwich product and how its convention and the reversion on the left side should be standard, okay? But many authors follow the opposite convention of clockwise instead. So this is just a remark for people who care about the details about these conventions and things like that. If you don't care about the great details, you can skip this, okay? But we're just gonna keep it moving. All right, so this is another example involving this Riemann sphere in projective geometric algebra. So let's define a set of points like this. Okay, let's pull up this formula. Where was this? This one, right? Okay. So these are just examples that I've had on my documentation page for a while, but they're now re-examined using the TensorField formalism of Cartan. So this just gives you the same plot as before, but now we treat the result as a tensor field like this, okay? Okay, tensor field. All right. So it's a Cartan tensor field, has an open topology. Okay, so we have all this topological FiberBundle tensor field stuff. Okay, and then we can just plot it. It's very nice. Very nice. This is a new formalism that's I've introduced in how to handle all this information. Let's try another example. So that was another one of those examples that I had on my documentation page, right? So we can now get the results here as a tensor field and study it like that, right? Like let's look at the curvature of it. Or I don't know. May not be very interesting, yeah. Let's look at the speed at least. Yeah, so it goes very fast at some point. Very interesting. Okay. Yeah, this. Let's take a look at this one. Yeah, so it's just another one of those examples. Let's see about the speed of this one. Okay. Yeah. All right. But these are using this exponential function, right? So this is a rather I guess complicated calculation in some sense. So uses exponentials and different kinds of operator compositions. All right, then let's look at the final example. So that was for the Riemann sphere projection, okay? Now let's do the conformal geometric algebra. It's taking a while for some reason. What's it stuck on? Some kind of error? Oh, right. It required I forgot you had to apply. Oh, I forgot to put that in there. Okay. There you go. All right, so we went through those examples. Let's move on. All right. So let's make a product space over 2 dimensions. All right. So we've got a domain now. And we can do something like this. Tensor. Apply it to the domain. So what this is doing is this is producing a tensor field. Okay. This is a tensor field. And then we just take the stream plot of it, okay? So, and we can modify the result of this by changing like this from pi to pi over 2, right? Oops. We need another parentheses somewhere, or what? I put one too many. Okay. There we go. So now that's the circular one. And we can change the angle now using that. Pi over 4, okay? And we can add a reflection to it. So those are just some of the standardized examples that I've discussed for a while, but you can deal with them in TensorField formalism now. So we have the same thing. But note that V here, this is the same line of code, but V is a different thing now. After we redefined the basis macro, V is now a different algebra, okay? Okay, so we've taken a look at some of these examples. Now let's take a look at three-dimensional examples. Okay, we need... So that produces TensorField. Oh, I forgot to close this here. All right. Something ain't right. Oh, did I misspell this? Oh. I put a times instead of a plus. Yeah, so I was a little bit confused because the output didn't look correct, and that's because I need a plus instead of a multiplication right there. All right, so there we go. Now we get the correct plot. So that's the plot right there. So this is the plot that's displayed in a lot of images related to Grassmann.jl. I like I like using this as kind of a representation of what's possible with Grassmann.jl. So this is that TensorField that gets produced from that calculation, right? So okay, so let's do VDOM 2. Oh no. There you go, there's this one. It's another interesting one, I think. All right, so let's get into this. So this is the multilinear n-linear Lie bracket. Okay, so while back I uploaded a paper where I proved that there's this multilinear Lie bracket recursion formula and what the proof of that formula is and what the how it expands into different into higher order Lie brackets. So yeah, so that's something I wrote about a while back. I made like a video discussing it as well on YouTube and published the paper and so on, and with the proof of the theorem. So I'm just gonna I have the theorem here just for reference. So if Lie bracket recursion is an n bracket is a sum of n minus 1 brackets, okay? This recursion can be explicitly explained from the unary rule like that, and then this is the typical Lie bracket, and then this is the ternary Lie bracket, and this is the one with 4 arguments and 5 arguments, and it can keep going. The multilinear Lie bracket recursion properly generalizes the bilinear Lie bracket to the n-linear case and is analogous to the Koszul complex of the Grassmann algebra, but is fundamentally different due to multilinear Lie bracket being non-associative, unlike the analogous exterior product. So not only was I discussing this in the paper and whatever in the video I published and all that and the proof and everything, I actually had this implemented in the programming languages as well. So let's do this example. F1 of x. Let's get the typing out of the way. All right. Chain of cosine of x of 1 times cosine x of 2. All right. So we've defined three functions here, f1, f2, and f3, and then we've expressed them as vector fields in some way. And now we're gonna apply the Lie bracket, okay? So Lie, so we have stream plot of VF1. Let's take a look at it. Stream plot of VF2. So we have the stream plot of these different things, right? So let's take the Lie bracket of VF1 and VF2. Okay, so that's what's depicted here. And when we switch between these two, it switches orientation. You see that? It's the same result, but the arrows point in the opposite direction. And not only that, but we can make a ternary Lie bracket. Okay? And it's not restricted to ternary. It can take another one as well, like, you know, like, do it like that. But that one doesn't look as interesting, I think. This is a pretty interesting one. And I like this one too. So I made them I think they're worthy of being examples, aren't they? For a multilinear Lie bracket. And I don't believe the multilinear Lie bracket is like a new idea, right? So the TensorField, the Cartan TensorField implementation with the geometric algebra and everything is a new thing, and then the multilinear Lie bracket is like a new thing I proved with the multilinear Lie bracket recursion formula, and I don't think like all these kind of features have existed in other like programming languages, at least like scientific computing. Like if you go into MATLAB, like your standard MATLAB or your standard, you know, Python or your standard whatever programming language you use, I don't believe it was standard that you would have like some kind of, you'd be able to do these kind of Lie brackets and stuff, like multilinear, like higher order Lie brackets too as well. Just casually like this, you'd be able to do them. So you can do them with my software. And so let's move on to the next thing for the integrals. Length of a line, area of disk, and volume of a ball. So let's take a look at this here. Let's create some kind of like lin space type of thing. From -2 oh, I need the equal sign, of course. Yeah. And then we can make a diameter like this. Now, what does this actually produce? Diameter. What? Did I spell it wrong? Oh. So this produces a line that's basically, that's 1 in the radius of 1 and 0 outside of that, okay? So we want to compute the integral of that. So if we integrate you know, it uses this approximation, you know, to do that. Anyway, let's move on to the next example. Not get too bogged down on every single example. So we now have a square domain. We do something similar to the diameter, but now it's going to be a disk. And what happens when we integrate that disk, you know? It's pi, of course, right? So this is what we've set up here. So this is just to show that you can calculate this integral, you know, of 1 basically, right? And that gives you the number pi, right? Because it's the area of the circle, but it's in yeah. So it's a nice calculation that helps verify that it works. And let's go on to the cube. So we integrate the ball and we get 4.19146, and 4 pi over 3 is 4.18. So it's a pretty nice approximation. Let's look at the volume of the ball. Or oh, I may have to. Oh, I was working on that the other night. Anyway, we don't need to visualize the ball right now. It's not a big deal. But I thought I set that up correctly, but that'll be fixed in the next version. It's always an easy fix. It's no big deal. It's gonna be working. All right. So now we have the hyperarea of a hypersurface. So let gamma be with a subset of x from Rn to Rn plus 1 be a parameterized hypersurface, which is a boundary of omega, which is gamma of x. Okay? And since the pullback of gamma star 1 is determinant d gamma, we can apply these really nice integral things, relations. So this is a theorem, okay? So we have the integral of over the boundary of omega, okay? And that's the integral of gamma of x, like the integral of 1 of gamma of x, okay, right? But then this is with the pullback, the integral of x, okay? So now we use a parameterized hypersurface to calculate this, and it's the absolute value of the determinant of this exterior product, okay? And x can be parameterized as a1 to b1, you know, if it's like a grid like this. The disk circumference and the sphere spat. So let's try those out. So that's our typical circle, right? And so what happens when we take the surface area? So we know that these are two different calculation techniques. Like, they give you pretty much the same answer, but total arc length calculates it one way and surface area calculates it another way. And it looks to me like the surface area approach actually has a smaller error. Okay, so this is the wireframe of the sphere, and we can calculate the surface area like that. So yeah, 12.533. So that's pretty good. And for circ, compare with 2 pi. So that concludes that example. So let's get to one of the more interesting results in this paper, which is the sector integral theorem. And I haven't seen this before anywhere else, so I think this is a new theorem. I don't know if it's been, you know, discussed somewhere else that I'm not aware of, but to me this is a new theorem that I found. So it expresses this kind of generalized sector integral. So when x is like a subset of Rn and gamma is a parameterized hypersurface, like previously, with gamma of x being parameterized in this way by x, and it's the boundary of omega. Well, the point is that there must exist some omega defining the sector of the hypersurface gamma of x with scale rho equals 1. So the question now is about what's that omega, and it's the integral, and what's the integral of it, right? So there's some omega and the integral of, like, we have this integral 1 over n plus 1 times the wedge product of the integral of the wedge product of gamma and d gamma dx1 and d gamma dxn. That integral equals the integral of 1 on some sector, and omega is the sector of the hypersurface, okay? And this is like the sector integral, and this is like this is like a formalism. So I have the proof here, so you may not understand why like this sector integral theorem is a thing, but it's because of this. First of all, because we can prove it in the following, and then it shows up in various calculations, and so that's why in the Cartan package. So because it shows up in various calculations, I figured that I'd discuss it like as a theorem and give the proof of it and so on, and how to think about it. So, all right. So if we'll consider a function like f, which is from 0 to row and the product with x. Like this is a product space from 0 to row and x to Rn plus 1. And it's defined like this: f of x0 to xn equals x0 times gamma of x1 to xn, okay? So it extends the function by adding another parameter to it. And now we want to take the integral from 0 to 1 of that the determinant of df, okay? And this expands out integral of 0 to row x0 to the n gamma wedge d gamma dx1 wedge d gamma dxn. And now we have to take the integral of this from 0 to row, and that makes it so that we have rho to the n gamma over n plus 1 wedge d gamma dx1 wedge d gamma dxn. And so this result then can be applied with a pullback. Okay, so since the pullback of f is determined df, then the domain omega is actually f applied to 0 rho to x, and we're going to set rho equal to 1 actually, but with a new variable. So that means that the integral of 1 over omega equals the integral of f of 0 rho, the product of 0 to rho and x, okay? And so we can use the pullback. All right, so now we have the integral of x and 0 to rho. So we can split up the domain, because you know how this is the product space, right? 0 to rho and x. So that's why we split up this integral now. And because we know what the integral from 0 to rho is, we now have the integral over x, okay? Because we evaluated this already. And now we can rewrite this using this notation, okay? So hence the integral over 1 of the sector omega is the sector integral covering gamma of x by parameter x. So yeah, I found that's quite interesting. So let's do it. Let's do sector integrate circ. Okay, so we can see now that doing the sector integral is a nice way to compute. Like we just apply the sector integral, and then that gives us the volume of the like sphere is just like a surface, right? So we have this parametric surface of a sphere, and if we take the sector integral of it, like I talk about in my theorem, then that gives you the volume of the sector inside of the surface, and that's the sector is like that inside of the sphere. But The sector integral theorem is like more general. Like this doesn't need to be necessarily a closed surface, I guess. But it'll still produce a domain, a sector. So there's a lot more to it with the sector theorem and stuff, but let's just keep it moving. So what about the link number example? So we have to define the link map of two space curves instances f of t and g of s as parameterized hypersurface link s of t equals g of s minus f of t. So we have the link map, and as a corollary of the sector integral theorem combined with the unit link map, we have the following integral: 1 over 4 pi of gamma of the sector integral thing equals g of s minus f of t divided by the absolute value of g of s minus s of t cubed, and then df dt dg and dg ds. And what's interesting about this is that this is 4 pi over thirds, so you can divide this by, it's the sector integral of the unit link map divided by 4 pi over 3. So that's the volume of the sphere, okay? So the link number is the sector integral modulo the sphere, okay? When the evaluated with a parameterized hypersurface, gamma of s is the link map, the unit link map, okay? So the link number defines the sector integral of gamma of x by the volume of ball. Let's try out some examples. So here's an example with two curves, f of t and g of t, and they're just circles in this situation, but they're circles oriented in three-dimensional space. And now what we want to know is what's the link number of those. And it should come out to 1.0, but because this is like a approximation, it's not exactly 1.0. It's an approximation of a numerical approximation of an integral. And we can also look at visualize what the link map looks like. So we had those two curves, and now we have the link map, which is of those two curves. Okay, so this is the surface that's being integrated in this link number example using the sector integral theorem, okay? And link number gives you the actual link number, okay? But link map helps us look at what the surfaces look like. Then we have the Gauss curvature. So it's alternative formulas for extrinsic Gauss curvature Ke and intrinsic Gauss curvature Ki with normal n. So if we take the unit normal map and use it to define Ke of x like this, and Ki is basically Ke divided by the norm of the normal. That gives us the intrinsic and the extrinsic. And with this formula, the Gauss-Bonnet integral is a sector integral theorem. So let's just get into some of these examples. So here's an example of a torus, and we use the normal norm map to color it basically. So like normal norm, you could plug torus, the tor object into it, or when you want to visualize it, you can plug it into the mesh function, okay? Or mean curvature. That one takes a little bit longer the first time at least to calculate it. Or the sine of the Gauss curvature. Some people find this interesting because it's the sine of the Gauss curvature changes on the torus and this visualizes that sign change. If you're interested in that. Let's define also this wobble. So I've previously shown this example before, but I figured I could keep this as an example. So we've defined the function, and then we just apply the function to a torus parameter on a 60 by 60 grid, and then we just visualize it again. But this time, because it's the torus had the function like this, now we changed the function to something different, and it highlight, or it illustrates more of what like here we have the Gauss extrinsic and the Gauss intrinsic. They have different brightnesses. You see that? And the reason for that is because this is a factor, this gets factored out in the intrinsic case, the normal norm. Okay, so the normal norm is present in the extrinsic case and factored out in the intrinsic case. And that's why we have all this going on. Now, another thing that's in differential geometry is when there is a Levi-Civita connection with zero torsion related to a metric tensor, then you have this relation with the Lie bracket, and there exists a Christoffel symbol of the second kind, gamma ijk. And in particular, these can be expressed in terms of the metric tensor G. So this is a formula that has been discussed many times before regarding the Christoffel symbols of the second kind. And then there's the local geodesic differential equations for Riemannian geometry, which apply these Christoffel symbols. So we're gonna do this in an example here. We're gonna continue from the previous example. So this is the intrinsic metric. So if we pick like 2 points on here, on the like 1.2, 1.3, that gives us an outer morphism of the metric tensor at that location, okay? And then this calculates the Christoffel symbols of the second kind. So in order to solve the local geodesic differential equation, we need an initial condition for the differential equation solver. And that's what we're going to create right now. And we're going to use these Christoffel symbols. Then we're going to pick a point on the parameter space. Then we're going to pick a direction or a vector. And then we're going to pick a time, a maximum time for the integral. Oh, we forgot to do using adapode. Okay, so there we go. So that's produces a geodesic condition. And that gives us the solution there. So now what's interesting is that this actual solution to the differential equation, the geodesic, it was in the two-dimensional parameter space, and it's only when we apply the torus back on it that we get the three-dimensional result back. So so it solves it in using the intrinsic metric, right? So it would appear that its length is, 74, but that's not correct. Let's define this right here. I can type it out. It's not a big deal. All right. Oh. So what's going on here is we've defined another TensorField, Sol M, and this has the intrinsic metric built into it, okay? And so when we take the total arc length, I've demonstrated this before in another YouTube video. When you take the total arc length of Sol M, that gives you the same total arc length as the solution on the torus. So using the intrinsic metric, so this is like a line, a two-dimensional line that goes through a two-dimensional space having a metric tensor. So at each point along the line, there's a metric tensor, and as it goes through this two-dimensional torus space, it has, when you take the integral, you have to take the metric tensor into account. And so the total arc length of that curve can contain that intrinsically. So you can either do it in the Euclidean metric, in three-dimensional Euclidean metric, or you can compute the arc length with in the space with non-Euclidean metric. And the formalism here allows you to do like a fully non-Euclidean, metric that varies from point to point, like this, the metric tensor on this, and this can be any general surface, okay? Let's look at the lines of the arc length. Yeah, and there we can see that what the difference is between the apparent arc length and the actual one. All right, so, but the thing is, this can be any numerical surface that we calculate these geodesics on. Like, we happen to be using these formulas to create these surfaces, but they can just be any numerically generated surface. Like, it doesn't have to be generated from a nice function. Like, but here's an example with the climb bottle. So we compute the Christoffel symbols for the on the climb bottle. And then we set the geodesic initial condition. Select a point and a direction. Select the time duration. And now we have our initial conditions specified. And wow, I mean, look at this initial condition. It's got a lot of data inside of it. Oh, I gotta capitalize that. Ah, forgot the X. Okay, so that produces the geodesic on the Klein bottle. But what we'd like is to visualize it on the Klein bottle. So there you go. And let's look at the wireframe. So this is a one-sided surface, and even though it's a one-sided surface, we can solve the geodesic differential equation on it, and it just keeps going on the topology. And although you could reach some kind of a stack overflow limit if you extend the time duration too long on this type of topology, the way it's currently implemented at least. And you can of course look at the normal norms. So yeah, and then we can put the geodesic line oh there you go. So we can see the line. Maybe, I don't know if red is a good color. white. Yeah, so we can see the geodesic on the surface here. And we colored the surface using the curvature. So that's a geodesic on the climb model, and you can, you know, change the initial conditions and all that, and try out different integrations and so on. And you can do it on any arbitrary shape, any topological kind of shape, parameterized like this, or whatever. Or let's do the upper half plane, intrinsic hyperbolic Lobachevsky metric. So there's this kind of half plane function that you can define. Yeah, let's just... Oh, do I not have Z4? Oh, was that capital? Oops, Z4. Z5. All right. So we can put like lines of Z1. Oh no, we don't want to put semicolon afterwards. Suppresses the plot. So this is just an example of trajectories in the hyperbolic plane, like geodesics on the hyperbolic plane using the intrinsic metric. Using this technique, you know, it's just another example of demonstrating different ways you can calculate different things. So let's take a look at the hop vibration, how you can manipulate that as an example. So here we have it, you know, parameterized in terms of three variables like this. Stereographic projection. And then there's a hop topology that gets applied here. Is it running out of memory or something again? Let's just start a fresh session one more time, since we have a lot of stuff going on here. It's unfortunate. Well, that command should normally work very well, but since it's not working right now, there's an alternative way we can get the same result. So let's just do that then. All right. All right. So let's zoom in on that. So this is that picture in the depicted here. So of the hop vibration. So this is a particular way of visualizing the hop vibration. Okay, so the different pieces of it and stuff. So, and yeah. Anyway, we'll not get stuck on it too long because we've been at it for a while. So let's get going. So there's a lot more you can do with all these things, but we just keep going right now to get through various things. Let's see, the sphere was defined. So we're gonna recall to so this is just a little fun example with the stream plot. Stream plot on a sphere. So we had this vector field, right? VF2, and we can put it on the sphere. So I don't know. This is a function. So the reason why I made this an example is because this is not like a default function you can easily do with a plotting software. So there's like some extra calculus that has to be done in order to transform the coordinates into the tangent space so that you can visualize a stream plot in the tangent space of as an embedding in the three-dimensional space. And so Cartan.jl helps make that possible. So and it makes for nice looking plots. Like, it's just interesting to look at, right? So definitely worth checking out just for that reason, like to try out the functionality and different things like that. Oh, that's an interesting one. I like that one. All right, well, we've kind of gotten carried away a little bit, so let's look at the Darius example. So the Cartan abstractions enable easily integrating this differential equation here. So we're gonna load Adapode. So now we have this line here. And we're gonna find the Darius equation. So that's the solution to the Darius equation using that initial condition. It's a very nice little solution right there. One thing I didn't put into the paper, but you can do here is so there you go. So the Bishop frame example, as an alternative to the standard Frenet style unit frame, the Bishop unit frame takes a space, curve, and an angle as an argument. So it has an optional angle as an integration constant, modular rotation of the tangent axis. What is going on? So there we can see what a Bishop frame looks like on this curve. All right, so let's try out this example, the eigenmodes of a disk. So with MATLAB this time, so we'll do using MATLAB. Yeah, we've already done that. So there's like this circle G mesh, which is one of the default meshes in MATLAB. We'll just pick that. Oh, I spelled that wrong. Circle G. All right, so now it should work. All right. So that's the wireframe of that. Then we'll assemble the stiffness and mass matrix. So we'll see that this is stiffness matrix, the mass matrix. So these are sparse matrices. And now we're going to use Krylov-Kit to solve this as a general eigensolve. This one might take a little bit longer on the first run or so. And the video encoding processor is running as well. All right, so there we go. Now we have the results. Now let's assign the amplitude to a TensorField. All right, so there we have one of these modes, and we can superimpose the wireframe. So there you go. These are these eigenmodes of the disk. So you can have these, you can try a different index here and you'll get one of these different ones, you know. So that's that example. And to build on the FiberBundle functionality of Cartan, the numerical analysis package Adapode is being developed to provide extra utilities for finite element method assemblies. For example, like a Poisson equation syntax or the transport equations with finite element methods can be expressed in terms of methods like volumes using exterior products or gradient hats by applying the exterior algebra principles discussed. Global Grassmann element assembly problems involve applying geometric algebra locally per element basis and combining it with a global manifold topology. So here's just some more examples of these finite element type of methods. that are in the adapode package. So like the Poisson equation, the algorithm can be, you know, split up into this, calculating these different things based on these TensorField inputs, and then so I mean, this is all fairly standard stuff, but this is just my particular implementation of it, and I like the approach that it takes. It just works well with all these different methods that I've been demonstrating, and yeah, so I don't know. So these are just some examples to show how it could look. More general problems for finite element boundary value problems are also enabled by mesh representations imported into Cartan from external sources and computational operated on in terms of Grassmann algebra. Many of these methods automatically generalize to higher dimensional manifolds and are compatible with discrete differential geometry. Further advanced features such as discontinuous topology have been implemented, and the Lagrange topology variant of simplex topology is being used in research. Let's take another look at an example, a heat flow around the airfoil. So in the flow geometry package builds on Cartan. So there's another one of these packages I made. This is just for my personal interest to provide the NACA airfoil shapes. So let's generate another mesh. So this is like a feature I created that will create like a representation of a NACA airfoil, like NACA 65511, that produces this type with this American NACA 4 convention with the Clark Y chord and so on. And this helped that, like, you could do I believe, yeah, that'll give you the lines of the airfoil. But we've made a mesh now. So this is the mesh with the airfoil. And I think I've demonstrated this before in another YouTube video somewhere. And these calculations, I've been doing these for many years, but I'm demonstrating them in this example now to show some of the capabilities that you can have. So this is just specifying some boundary condition data using geometry information. The exact meaning of all this is not so important, to just oh. Oh no, this is the example they gave. Stream plot GTF negative 0.3 dot dot 1.3 negative 0.2 dot dot 0.2. That was okay. Yeah, there we go. So that's the command for the stream plot. All right, let's define the function for kappa of z. Okay, so we're just gonna recall that. Okay, and so now that was solving the transport diffusion. So that was the heat flow around the airfoil. So that was just to demonstrate some of the finite element calculations, kind of standard. It's just to give an example. So those are some of the. So that was the solve Poisson and solve transport diffusion example. Just to show how it works, and most of the finite element methods using Grassmann and Cartan, they automatically generalize to higher dimensional manifolds with tetrahedra, for example, and the author has contributed to packages such as triangulate.jl and tetgen.jl. So let's try another one of these. Oops. Gotta spell it correctly. PS, that was the name of it, yeah. So now we have this sphere, and we're gonna use that to tetrahedralize a mesh around the sphere, actually. So tetrahedralize cube sphere. And it's gonna have holes specified in it. So I forgot to export cube sphere over here. I guess I'll export it sometime in the future. So the way to fix that right now is to add flow geometry dot cube sphere, but it will be exported in the future, I think. So I just have not actually exported it at this time yet. So, but for the sake of these examples and so on, I should be exporting it. Dang, man. Something's slowing down my computer today with this video processing, huh? So there you go. So that produces this three-dimensional flow example around the sphere. So that was just another one of these examples that we're going to cover. So Maxwell's equations rewritten. Cartan has Nedeleg edge interpolation useful for solving the time harmonic wave equation. So we can form Maxwell's equations using the Faraday bivector dA with dDA equal to 0. And I've solved this as a finite element method, showing a picture here, like as an example. We don't have the example here in the paper for this particular one because it's more complicated. But I've discussed this before previously in another video in another paper. So dDA equals 0. And we have Gauss's law and Faraday's law. And we have star d star dA equals J for Gauss's law and Ampere's law. And so then the Maxwell's equation simplified to a single space-time wave equation. This is the same thing I've discussed previously. So I've included this again one more time because I think it's an important piece of information to consider. So let's continue on to the final example here. So Stokes' theorem. So we consider a paraboloid S equals gamma of x bound by a compact support disk of radius 3 with a circle f of 0 to 2 pi, which is the boundary of S, and this vector field F. So this is just a nice example that we're going to take a look at right now. So we're going to produce a square and a cube. And now this is the compact support disk. So we have this disk. This just ensures that we're within the radius of 3, okay? So that's why we have the disk here, okay? And then we're going to define the paraboloid. And then define what S is. So S is this paraboloid restricted to the circle, right? So we're just cutting it off right there where the circle is. Then we define chain f of x. Yeah, so I already plotted that, right? And then we can add these scaled arrows on it. All right, so those are some unit normals right there. Okay, and then this is the stream plot that's around. This is the vector field that's around this paraboloid. And now what we want to do is we want to calculate this integral here. So this is integral of the curl in terms of the normal. So this is a surface integral. So we can apply the curl to f on the cube and then evaluate that on s. And then integrate that. And we get 56.5474. Then we'll do an integral around the circle. And now we can integrate this as a line integral. We can, the integral from 0 to 2 pi of f of t and f prime of t. So f dot t all right, let's integrate this. All right, so now we computed this integral in two different ways, 56.547. Now the exact answer is supposed to be 18 pi, 56.5486. So yeah, it's a nice integral approximation. We have these two different integrals, and we can see that the result is the same. And we computed it numerically using these TensorField representations. So you could technically verify this using just any general tensor fields. It doesn't have to be generated from a paraboloid that's like a nice formula like this. And it doesn't have to be a vector field that has a nice formula like this. These methods work in general just using any FiberBundle representation that's used here. So yeah, so that's a nice example. Both integration techniques come out to the same answer. This is called Stokes' theorem, a special case of the more general Stokes-Cartan theorem. So I thought that's a nice example to wrap things up with for now. And so To summarize, Grassmann.jl and Cartan.jl pioneered many computational language design aspects for fully generalized high-performance computing with differential geometric algebra. All of the mathematical types and operations in this program were implemented from scratch with fundamental mathematical principles merged to Julius type polymorphism code generation, which has been refined and is being optimized for scientific computing over time. This leads to the capability for multiple dispatch polymorphisms with type aliases such as scalar, graded vector, bivector, trivector, and also quaternion, simplex,